There we go. Audio. Ah. Oh, all right. Any questions before we get started? So we're probably just going to go over the quiz first and then go from there. I don't know why my video isn't working right now, but let's just go through the quiz. So starting with chapter 15. So what do we get for number 1? So blood, smoke, milk, fog, shaving cream, what are all those? What do we say? What do we say? I didn't hear it. Yeah, colloidal mixtures. So do we all agree? We could take votes. All right, colloidal mixtures, good. So number 2, so like I promised, right, I'm not necessarily going to be consistent on the unit, so always just watch your units with all of these. So we could work this out if we needed to. Otherwise, what do we get for our answer here? C, do we all agree with C? Okay, excellent. C. And like I said, if we need to work it out, we can. Just kind of a quick rundown, right? Okay, so would like to see it worked out. So let's do that. Sorry, still trying to get my camera going, but I'll work on it later. All right, so we're given our molar amount. So let's just think of our separate steps. So first we have to heat our ice from negative 22.5 degrees Celsius to 0, right? That's our melting point. Then we're going to melt at 0. And then, okay, it says to stop there. So I'll pull up my calculator as well. And so then we need to look at our specific heat, right? So this is our heat capacity for heating our water. And again, it's given in moles this time, unlike I think we saw previously. And so now we're given it in moles, so 0.25 times our heat capacity of ice, so 37.7, times our change in heat, so 20, or change in degrees, so 22.5. So remember, you have the same temperature difference in Celsius as you do in Kelvin. All right, and then watch the units though. So that's in joules, right? So that is 0.212 kilojoules for that process. Questions? And then, so now we're going to melt it. So our heat of fusion is 6 kilojoules per mole. So 6.01 times 0.25 since we're in molar amounts. And so there's 1.5 kilojoules for the melt. Then add the two numbers together gives you about 1.71 kilojoules there. Questions on that one? All right, next one. So number 3. How does metallic bonding differ from ionic and covalent bonding? So anybody like A, B, C? So it looks like everybody likes C and D. Okay, so no one liked D. So yes, like we mentioned, those delocalized electrons going across our bonding, right? So we essentially have a lot of whatever our orbital is. So if we're talking about sodium, a lot of 3s orbitals, right, that all make your conductive band. Good. And so then definition, solid, liquid, and gas of all the same substance are in equilibrium at, so is it called the critical point, the melting point, the triple point, or the boiling point? So somebody yell. So triple point, so good. And then that may also be like a diagram question, where you'll have to identify the triple point on a graph, right? Just label it. Oh, so this is a definition 1. So how many total atoms in a body-centered cubic? So I hear 1. Do we all agree with that one? So double check that one. So the body-centered, it's kind of like this one, right? So it has kind of 1, 2, 3, 4, 5, 6, 7, 8, right? So then that's 1/8. And then you have your centered in the center. So then, yeah, that should give you 2 total. So kind of tricky. Questions on that one? So just have your notes ready. All right, so 6, what best describes our equilibrium vapor? So any votes for A? Liquid continues to evaporate, but no condensation. B, any votes? I see lots of votes. So evaporation and condensation occur at equal but non-zero rates. So that sounds good. And then, so neither evaporation nor condensation occurs. So that doesn't make sense, right? So we do have molecules coming out and also coming in. And then again, same thing, right? Doesn't make sense. Our vapor continues to condense, but no evaporation, so no. Okay, so again, they're going back and forth at our equal non-zero rates. And I see chat agrees. Which of the following halogens has the lowest boiling point? So mass argument there. So which one has the lowest? So fluorine. And so again, right, it's a mass argument. You could also just think back to the periodic table. You remember iodine's a solid, fluorine is a gas. Right. Which one is an example of an ionic crystal? So of course, right, ionic being your key word. So is it glass, salt? So I see lots of yes. So sugar, right, not ionic. And then diamond, so same thing. Again, not ionic, so molecular crystal there. And sugar is just a molecule. 9, so another definition question. So which of the following properties best explains why liquids tend to draw themselves into spherical droplets? And so is this surface tension, capillary action, viscosity, or dispersion? What did we say? Sorry. Surface tension, A, excellent. Questions on that one? And again, we can think back to the penny demo for this question. Oh, this is a good one, so you guys can give me your thoughts. And so kind of what is it saying, right? Break down the criteria. So it wants us to pick a molecule with London forces. And this is just a reminder, right? Everything has London dispersion forces. And then dipole, dipole. So what kind of molecule are you looking for? So polar, right? But we can't just pick water. So it said no hydrogen bonding, so we have to be a little more creative. So what did you guys pick? Any thoughts? So SO2 would be a good one, right? So that's polar. Sorry, what else did we say? So formate, or yeah, that would be a good one, or any other derivation like acetone. So formate acetone, is that what you're saying? Yeah, this one. Yeah, formate. And this is acetone. Good. Other examples, general ones? Personally, I was also thinking of the dichloromethane one, or chloroform, right, where you just have one Cl, so one or two, or you could just draw one. Uh, I mean, you could go crazy. Acetonitrile. So just as long as you don't have a hydrogen bond. And so in the past, that was kind of the area where students got this like wrong, was they knew it had to be polar, but then they would still accidentally pick like a hydrogen bonded molecule. But so good examples. Any others that we want to touch on? All right, so probably what I'll do, I'll grab like a sheet of paper and have like people put their name on it so we can do like a completion grade in class. So I'll take a grade of who's here. And then we'll do that for 16. So I guess you'll get a double bonus. So let's go over those. I just forgot to grab a paper. All right, so let's start with number 1. And so remember, this goes back to where I was like, this is basically the opposite of solids. And so which one of our statement matches here? So any votes for A? So no. So B, C, D. So I see everybody likes D. And so like we went over, they tend to be more water soluble at lower temperatures, right? Get that more dissolved. Again, you don't have those unfavorable interactions. So like we mentioned, nonpolar plus our liquid does not really mix well. So once we get higher energy, it comes out of solution. And then like you saw with the formula, higher pressures, which again makes sense for canning. I don't know if anybody does their own soda or canning in here. Oh, nice. All right, so what's our expected Van Hoff factor for sodium phosphate? So 4. So are we, yell it out, everybody? Good. I'm just going to keep moving. So which of the following is not true of an ideal solution? So let's just go through. It has solute-solute interactions that are equal in strength to its solute-solvent interactions. So is that ideal? So yes, okay. It follows Raoult's law, exactly. Well, yeah, that's the definition. It can be closely approximated by a dilute solution. So yes, right, that's our math. And then it forms an azeotrope during distillation. So I see some no's, right? And so that is the kind of opposite definition of an ideal solution. And like we kind of touched on in class, that azeotrope is forming because of really strong solute-solvent interactions, like we saw with our ethanol, right? So a lot of hydrogen bonding that really stuck together. And like we mentioned, that's a constant boiling mixture of about 95% purity. All right, another definition question. So what does isotonic mean? So any votes for A, B, C? So everybody likes C. So isotonic, meaning the same amount of particles, so same osmotic pressure, so they will neither swell nor dehydrate. Excellent. So which one has the highest freezing point? And before we start shouting answers, what's the secret to this one? What do we have to do and analyze? So Van Hoff factor, so that's one thing. And then, what did you say? Oh, so that gives us our moles. And then the other thing I'm thinking about is this all leads to freezing point depression. So, right, we're not really going for the greatest number of moles, right? That would give us our lowest freezing point. We're looking for our highest freezing point. So just make sure you know what we're looking for. So I'm going to write out our effective molarity, right? So 0.6, and obviously just double check my math here. 0.5 times 2, so 0.3. 0.12 times 3. So does that look okay to everybody? And then that would make our least amount of C. So then that would have the least effect of our freezing point there. Okay, questions on that one? All make sense? All right, let's try 6 then. So same sort of thing. And maybe you're thinking boiling point elevation in your head. So again, calculating effective molarity. So just double check me that I don't do something. And so then the highest boiling point should have the greatest moles. So it looks like B for my calculations. And so just double checking, yes, yes, yes. Any questions on those? I don't want to move too fast either. Definitely stop me if you have a question. All right, we'll finish out our quiz. So which of the following is not a colligative property? And so is it A, osmotic pressure, B, freezing point elevation? So I see some people flag that one. Vapor pressure lowering. Well, that's true, right? Because your vapor pressure of your solution is less than your pure. And then boiling point elevation, so you, right, that's pure. That's correct. So yes, it was B, and so this was tricky in the past. So again, it's freezing point depression. So that's why that statement was incorrect. That was a tricky question in the past. All right, 8. So what do we get for this one? So percent concentration, so notice it's just weight by weight. So it should just be 4 divided by 246 to get our percentage. So the way I think they wanted to do it is like weight per weight. I mean, I guess it doesn't make too much of a difference. So that's kind of the tricky thing about some of these weight per volume. So I guess it's probably over the whole, because sometimes it's not clear whether it's like a ratio or whether it is like a percentage, and like sometimes you have to watch the writing. So yeah, probably better to take it over the whole then, but it should be around 1.6% for that one. And then this one wasn't too bad, so we want 100 mils of a 0.25 molar solution. So we take our molarity, 0.25, multiply it by our liters, 0.1. So that's our moles, and then multiply it by our mass. So I'm kind of estimating. I think I'm probably off. So do we get D for this one, or did I mess up somewhere? Yeah, so let's do this one. Let's see, what did I screw up on? All right, so we want to make a 0.25 molar solution, and we're trying to make 0.1 liters of it. I probably just have my mass of sodium chloride wrong. That sounds right. So 58.443. So yeah, I was off. I don't know what I was thinking. So trying that again. So 0.25 times our liters. Now multiply it by the correct molecular weight. So 58.443. And so yes, that does give you B, again, now that I have the correct molecular weight. So does that make sense for that one? All right, so let's try 10. So 10 could have been tricky. This was another one of those finding the mass from our molality ones. So we have 8.88 grams of an unknown sugar is dissolved in 100 milliliters of water, and we get our new freezing point, right? So that's our freezing point depression. And then they do give us our KF. And so again, right, that's our difference from our freezing. And so let's set this up so you guys can walk me through, check my math. So our change in temperature at freezing is going to be equal to our KF times our molarity. So that means we have 0.74 is equal to 1.86 times our molality. Sorry, I misspoke earlier. Molality, right, from our symbol. And so let's go through that. So 0.74 divided by 1.86. And so I get this for our molality. And so molality equals moles over kilogram. And so now let's figure out, so I'm going to figure out how many moles was in this sample. Yeah, since it's sugar. So yeah, it's correct. It's not going to disassociate. Yeah, because otherwise you just like calculate for it in the end. Yeah, so what I would do if we like had known, well, the thing is we'd have to say like how many particles it would disassociate into and then like change that, like your molarity. Yeah. So is equal to, so 0.398 is equal to, and so now I want to figure out how many moles are in. So we had 100 milliliters, which is 100 grams, right? So 0.1 kilogram. So how many moles are in there? So that means 8.88 grams is equal to this many moles. So then we can divide, right, to get our molecular weight of our sugar. So about 223 there. Do we all get that answer? Any questions on that one? All right, so those were the quizzes. So do we feel relatively okay about the quizzes? Yeah. I mean, I haven't quite decided, to be honest. I mean, I have a midterm, right? But I'm gonna see how the midterm review goes and how I feel, and yeah, because there'll be a mix of multiple choice, there'll be a mixture of free response. So with that, let's do kind of a good free response preparation question. So let's look at these and try to use MO theory. So this would be like you'd be expected to do on an exam. And so look at our bond order of NF, NF plus, and NF minus. And then there'll be other free response questions, but like I said, I'm not sure exactly what mix I'll land on. But let's start with this one. Yeah. Oh, yeah. Yeah, I mean, really both, right? So the question is just kind of asking for it written out, right? But I would still do your MO diagram to answer this question. Because you still need a MO diagram either way. But your exam will probably state more explicitly to like draw out an MO diagram. So then how many valence electrons do we have? Let's just start with our NF. I'm trying to draw it in purple. So how many electrons do we have? Again, just looking at our valence. So 12 electrons. And so what did you notice about this species? So what does it look like? Does it remind you of something? So that is paramagnetic. So similar to oxygen in electronic structure, right? So 12 electrons, just like oxygen. And so, yeah, we expect it to be paramagnetic. And so then if we lose an electron, so now we'll only have one unpaired electron, an odd number. So I'll probably just fill it in next to it in green. So NF plus. So now we still have a paramagnetic compound, right? So still have an unpaired electron. It's just 1 versus 2. So now 1 unpaired. And then, so now we could, of course, add another electron and still predict it to be, right, 1 unpaired electron. So now we'll do NF minus. Oops, sorry. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then 11, 12, and then, right, these would be paired. So still has 1 unpaired in our pi antibonding. And so notice, right, that's all the action is, whether you have 2, whether you have, I'll kind of draw this a little better, 1 unpaired or 1 still unpaired, but then 1 paired there. And then, like we saw, all paramagnetic. It's just a question of whether they have 2 or 1 unpaired electrons. So that's pretty interesting. Other things that you might be expected to answer on an exam, I don't know if we want to go over all of them, but calculating your bond order. So remember, that's number of the electrons in bonding minus antibonding over 2. So maybe let's at least try that for NF, just the neutral case. So see if you can calculate our bond order for that one. All right, so what do we get for our bond order? So count them up, right? 1, 2, 3, 4, 5, 6, 7, 8, right? In bonding, double check me. Minus 1, 2, 3, 4, right? In antibonding. So we should get a bond order of 2 for NF there. And so just as a fun aside, this is a pretty unstable molecule, so it's only produced in the gas state. And as the bond order here implies, it does indeed have a bond order of 2. And I think we've kind of mentioned this in class, right, that that's generally not considered kind of correct most of the time. And then how else? So we need to put 12 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I believe, is how that goes. And then obviously that's unusual since we have 1, 2, 3, 4, 5, 6 there. So that gives us negative on our nitrogen. 1, 2, 3, 4, 5, 6. So formal charge positive on fluorine. So you can see, right, that also is going to kind of make it unstable. So it's a short-lived species, but kind of cool. Yeah. Only if I say, like, draw the Lewis dot structure. Yeah. But I'd probably want to give you a hint and say that because this is like a weird one, right? And like I think I spent most of class being like fluorine only has 1 bond. And then we're like, oh, look at this weird case where this is actually considered a double bond. So that is the fun of chemistry, though, is again looking at those kind of exception cases and then explaining like, well, yes, this is an exception case. We don't see that, and that's also why it's rare, it's unstable, and this is like fleeting in the gas state. All right, let's try. We'll go back. We'll do some simpler review. So starting with chapter 8. So which one of these are tetrahedral? So try to draw that out, and if they're not tetrahedral, what's the shape? So take a few minutes for that one. All right, let's go over them. So what is A's shape? So square planar. Good. Right, you can kind of do that quickly. So 8 valence electrons, 4 are involved in bonding, so that leaves you 2 lone pairs, so square planar. Good. So try that for B. So B is kind of tricky. What geometry did you get for this one? Yep, somebody said it. So again, same trick, 8 valence electrons. So we have 2 oxygens there, and then fluorine, fluorine, but that's 1, 2, 3, 4, 5, 6. So then we have a pair of electrons. So what's the geometry again? Somebody said it. Say it louder. Yeah, seesaw, sawhorse, teeter-totter if you really wanted. Yeah, good. Whatever. All right, what about C? NFO. Yeah, we finally found our tetrahedral shape. So good. So nitrogen, right? 5 valence electrons, 2 involved in the oxygen bonding, and then 1 in the fluorine. So there's our 5 valence electrons. Tetrahedral, yay. And then our last one, selenium tetrafluoride. Which one was that? Teeter-totter, sawhorse, yay. Yeah, it can happen with nitrogen and oxygen. Yeah, because it's kind of, you. It's really just that scenario. I know we don't see too much on the second row, but yeah, they can make like double bonds like that. All right, let's see. That's kind of a similar question. Okay, let's look at this one. So, which one of these have polar interactions? So take a moment. Oops, sorry. All right, so what do we think for 13? Which ones have polar interactions? So chlorine, right? That's not going to be polar. So that's pretty much non-polar. Chlorine, fluorine. I mean, not really, right? I mean, you could argue there's a small difference in polarity, but they're still two of the most electronegative elements. Nitrogen and fluorine, how about that? And right, don't forget with this structure, not only do you have your small difference in electronegativity, right, but you do have a lone pair, so that drives your polarity. And then, of course, fluorine, again, another nonpolar diatomic, so no. Good. 13, which one have London dispersion forces? So taking a look, so water, is that dominated by London dispersion? So no, right, that'd be hydrogen bonding. Helium, is this dominated by London dispersion? So yes, right, that's all it has. So going back to the mass argument for the boiling points of gases. What about chlorine? Yeah, say it confident. You guys, some of you are looking at me. Look, yes, right? Nonpolar. So it's mainly London dispersion forces once again. What about HCl? So which one does HCl have? So dipole, excellent. Yeah, so helium, right, it goes back to everything experienced London dispersion forces. So helium, since it's completely nonpolar, that's the only thing that it has dominating it, right, is the London dispersion, since it has, yeah, yeah, because it's only due right to the temporary dipole of those electrons spinning around. So yeah, it's only the London dispersion. But to your point, right, it's super tiny, and that's why it has a really, really, really low boiling point, right? Because it's really tiny. There's no surface area, so there's hardly any dipole-dipole interactions. So yeah, it's going to be a gas at extremely low temperatures. All right, 15. So which one of these can form hydrogen bonds? So take a second. Can H2 form hydrogen bonds? So no, right? What about HF? Can that do it? So yes, right, that matches our definition. What about CH? So no. And then what about our methanol, or sorry, ethanol here? Or methanol, I don't know why, I said the wrong thing. So yes, right, from our OH. And hydrogen bonded to nitrogen, oxygen, or fluorine. Let's do one more really quickly, then we'll do a little break. So look at these and see if you can arrange them by their boiling point and kind of note what's different about them. Oh yeah, and question in the chat. So just a reminder, right, there's no official lab this week, but if you missed the lab, be sure to make it up, so I'll be available today to do makeup labs. I'm also around, right, good office hour time. If you have other questions lingering, we can go over that. All right, so which one do we expect? And I don't know which way is lower for y'all to start, but which one is either the lowest or the highest? Sorry, what did you say? So yeah, neon, right, is going to be our lowest here. And that's our mass argument. And also, right, layering and nonpolar. And then what's going to be next? So I'll put this as 1. So C2H6. So again, pretty small and nonpolar as well. And then what's going to be next? So kind of have to figure out what's the difference between KBr and this ethanol. So ionic, so yeah, we have our special ionic solid, so this is the highest, and then methanol as our molecule with hydrogen bonding, right, is next, or ethanol, sorry, I keep screwing up my organics. Well, let's probably take a quick break or so, 5 or 10 minutes. And then we'll go back to review topics. So if you have specific questions, just let me know. Otherwise, I have some prepared questions. All right, let's try this one as we kind of come back from break. Might be a few stragglers.
So the size of the unit cell can scale.
Or like, yeah, I mean, for this one, you want to look at the individual atom, though, right? Like, it's always of the atom, but. So yeah, try this one out, right? Make sure you have your relevant information, how many atoms are in there, what other relationships do we need. So I'll still give you guys a few more minutes to work through this one.
I definitely have some things to talk with you about after class.
Sounds good. So start walking me through this. What information do we need? What does this tell us? Yeah, essentially, or like, cause well, I still think of it as mass per volume, but yeah, like you're gonna have to, like you're saying, take the atomic weight, and then yeah, 6.022 times 10 to the 23rd. Sorry, just catching up. So good, and then divided by our volume. Sorry, or mass over density. So that looks good. So sorry, I'm just kind of catching up. So density equals mass over volume. So yeah, and then, so how many atoms did we say? So 4, yeah. I'm just making sure we're all on the same page since we went kind of quickly there. So yeah, I'm going to do basically what you said. And then I want to solve for volume. So mass over density. And then silver is 107.9, right, for the molecular weight? So plugging that in. Oops, sorry. Divided by 10.5. All right. And then, so solving for this, right, so we're all on the same page. So volume is then equal to 6.83 roughly. And then we're in grams centimeter cubed, right? So this is centimeter cubed for volume. So again, that's also length square cubed, right, for volume, and length being edge length. So first I'm going to find my cube root. So take it to the 1/3 power. And then I get this, right, for my edge length of each cube. And then we have to go back to our notes. Let's see if I can find them handy. Otherwise, I have the formula. So here it is. Yeah, looking back, right, that the length is equal to 2 times 2 square root of 2r. So now we can go back and plug that in. So this is L. And so I get about 1.44 times 10 to the negative 8 centimeters. For our radius then, right, of our atom. And it only asks us for the edge length of the unit cell. So I think I went a little beyond, right, and calculated the R. So I probably should have read the question, but yeah, stop there, but then had it asked us to calculate R, right, we could have done that as well. Questions on this one? I feel like you guys are getting faster at that. Yes, no? All right, let's try some other ones. So how do you do this one? Calculate the density of chlorofluorocarbon at 0 degrees Celsius and 1 atm. What is that equal to? Yeah. So what information do we need? And then what should we recognize to make our lives a little easier? Yeah. Or mass, yeah. Mass over volume. Yeah. And then what's volume, right? What is this saying? Yeah, so that's what this implication is they're telling you that this is STP. So good, 22.4 liters. So we're putting the pieces together. And now we just need to calculate our molecular weight. So whenever people have some numbers. Why do we need R though? Yeah, we don't need to do it though. Too much work, right? Because we said we're at STP. Because, yeah, otherwise, right, you're going to go, oh, PV equals nRT. But, yeah, it doesn't really tell you moles. R is just your gas constant. But yeah, we should just assume STP. That's what they're trying to get at. And then what's our molecular weight? What do we calculate? 121.01. So 121.01. I have about that. So somewhere around there. So that looks good. So mass, so 121.01 divided by our volume. Again, assuming STP conditions. And so that gives us 5.4 grams per liter then for our density. Okay, sound good? Let's try this one. I know the partial pressures somewhat trick people. So we have two bulbs connected by a valve. One has a volume of 650 milliliters and is occupied by nitrogen. The other one is 500 milliliters and oxygen at 732 torr. So the valve opens, the gases mix. So what is the total pressure and partial pressures then? So how would we calculate this? So how is this one coming? And kind of how should we approach it before we just start diving in? Kind of how do we treat these problems? Yep. So yeah, let's do that. So kind of each gas at a time, right? No. Oh, too late on that one. All right, so good. So just like he was saying, right, let's just treat each gas separately. And then this can become just a P1V1 equals P2V2 problem, right? We're just calculating. We have an initial volume, and then let's get our final volume, right? So we're kind of treating each gas separately. So they're in their separate containers, and then let's get our final volume. So 650 plus 500, so 1150 for our final volume. And so yeah, so then we can just do P1B1 and then get our new pressure and then add them at the end there. So let's check how y'all did on this one. So just looking at our nitrogen, and right, units don't really matter as long as we're matching with this problem. So 650 milliliters, and we're at 825. And so now when we're at 1150, what's my new pressure? So y'all can help me out. So I get about 466 torr, right, for a new nitrogen. And then let's repeat that, right, for oxygen. Switch colors. So oxygen, same thing, except it was initially at 500 milliliters at 732 torr. So now we're going to find our new pressure. Volume still 1150. So new pressure of about 318. And so then let's calculate our new total pressure. Right, so we found our partial pressure of each. So now new additive pressure. It's about 484 or so torr. Not 484, 784. I don't know why I can't read, sorry. 784 torr. Questions about that one? Hopefully we feel a little better about those. Let's try a different type of problem. So now let's look at this drug. And so let's identify our hybridization at those highlighted ones there. And so I don't know if we went over organic structures that well, but something to keep in mind, right, is every point here is a carbon, and every carbon needs 4 bonds. And so like in this case, for example, 1, 2, 3, make sure you fill in your hydrogens, right? So that's something to do with organic structures. So write this little C there. So this is a carbon, but then it needs 4 bonds, so we know this is a CH3 group. And these are all CH2, CH2. All right, I'll let you finish. So what's the hybridization, again, at all these highlighted points? All right, let's see how we're doing on this one. So let's start with this carbon here. So what's our hybridization, right? So it's this little carbon, hard to maybe even tell, right, that there's a carbon there. How many things is it bonded to? What's its hybridization? Yeah, yeah, so carbon, nitrogen, so good. So two things, so then what is it? So SP, excellent, right? And again, you can kind of see that it's drawn SP and linear, but yeah, that's all. No, no. Although, right, you should be able to do that. So then we could do, well, there's 1 sigma, 2 pi. So, uh, but yeah, so that would be like the most I would ask probably. And then let's look at this one. So this carbon, right, is bound to 1, 2, 3 things. So what's its hybridization? sp2. Questions about that one? And then, right, we have our carbon here. So how many things is it bonded to? What's its hybridization? sp what? sp3, right, bonded to 4 things. 1, 2, 3, 4. sp3, so tetrahedral. And, oh, just for completion's sake, I forgot to say it. So, right, 4 sigma bonds for this one. For here, we have 1, 2, 3 sigma, and then a pi, right? Depending on what I ask on the exam. And then, so what about this carbon? What's its hybridization? Yep, sp3. So good, right? Again, you're kind of thinking about how you're going to be super prepared for OChem because you're imagining this in 3D, tetrahedral, tetrahedral at every shape. So good. And again, we can say there's 4 sigma bonds in there. And then what about this nitrogen? How many things is it bonded to? Double check your electrons though for these guys. So not a radical, but what's not shown on there? Yeah, so the lone pairs, so don't forget about those lone pairs. And so what's our hybridization? So what do we say? Sorry. Yep, so sp3 hybridization. And so, right, technically 3 sigma and then a lone pair there. Yeah, so that's, yeah, so this is a methyl group, and I try to draw out the 3 hydrogens that were attached to that methyl group. But yeah, just weird sticks are methyls. All right, let's see. We might have time to do both. Let's. All right, let me see if I can copy this page. Yes, yes, that actually copied. Okay, so like I said, I'm probably going to be mean and give you not water on the exam. And so this is benzene. I guess we could just do the first one here. Trying to zoom in for y'all. And so like I mentioned on the exam, I'll give you the relevant constants that you need. Like the exam, I don't know what unit they'll be in, so these ones are in cals and kcals, and they vary, right? This one differs between cals per gram degree Celsius. This one's kcal per mole. So again, just be aware, right? Got to read. So try the first one, and then I did give you the relevant melting points. So again, I would do that on the exam. I might be mean and put them in different units though. So just be prepared. So here's the melting point and here's the boiling point. So what heat flow is needed when 15.6 grams of solid benzene at 0 degrees Celsius are converted to liquid benzene at 5.5 degrees Celsius. Uh, 2.38 kcals per mole there. So benzene, probably on an exam, I should have given you the formula. Oops. Or maybe I'll give you the molecular weight. So I'll let you finish. And then for this one, right, we're not changing the temperature at any point. We're just literally doing the state change. So we just need our fusion. We did need to convert to moles, right? So kcal per mole. So just kind of double check me on this. So solving for 15.6 grams of benzene, converting that to moles of benzene. So about 0.2 moles. And then we can take that, right, multiply it by our heat of fusion for our state change. And again, right, just notice how your units cancel out for the moles. Oops. And again, watch the units since this is kcal. And so I get 0.475 kcal. So did we all get that for the first one? All right, so that one wasn't too bad. So now let's do, oh yeah. Correct. So this one, right, we didn't do any temperature change though. So we were at 0, so we started there. Oh, my bad. You're totally right. So, yeah, I didn't catch that. So then we need to warm it up. So we need to go, so solid needs to go, sorry, from 0, you guys were on top of it, to 5 to do the state change first. And so let's see, so heat capacity, it's in grams of our solid. So then 15.6 times 0.2, but then that's cals, right? So divided by 1,000. So 0.003 for the warming. Oh wait, no, I didn't multiply it. Sorry, I'm all over the place today. Let's do that one more time. 15.6 times 0.2 times our temperature difference. So 5.5. There we go. And so now that gives us, but like I said, that's cals. So 0.017 kcals for the first part, sorry. And then now we can add it up to get our total heat flow. Of about 0.492. Does that sound better now? Sorry about that. So don't be like me, right? I got confused myself just kind of looking at 0, and then I forgot that we're not looking at benzene, we're looking at water. So just, or said that the opposite. We're looking at benzene, not water. So just be very, very careful with all of that. So do we want to do, so we could do 22, or we could do another one of those, like figuring out the mass of a protein based off of the, we could do it off of the osmotic pressure. I don't know how people are feeling, or if you'd rather do another heat flow one or try to do both. All right, let's do 22 then. So calculate our heat flow. So now we're going from 0 degrees Celsius and cooling it to negative 10 degrees Celsius. So keeping in mind your melting point. So just kind of sketching it out here. So doing the first part, right? So just taking from 10, cooling it to our melting point of 5.5. So I got 0.025 kcals. So again, just make sure, double check my numbers. Then we'll do our melting, but right, we have to convert to moles. And so now we have to take our 13.8 grams of benzene divided by 78.11. So that gives us moles times, again, heat of fusion, so 2.38 for temperature change. So about 420 calories, or 0.420 kcal. And then finish the rest of it. So now heat capacity is for solid ice, so 0.2 times our temperature difference, so 5.5 minus -10 times 13.8 for grams. So about 42 calories, or 0.042 kcals. And again, double check all my numbers. So now we'll add up for our final answers to 0.0255 kcals plus 0.42 plus 0.042. And so I get about 0.4875 kcals total. Questions on that one? feeling okay about that one? All right, so I'll pull up kind of the last one that I have prepared. So just, oops, sorry, that's not, come here. No, sorry. Why? Oh, there we go. Okay. Sorry. I don't know why it took forever to populate. So pepsin is our digestive enzyme. And so we have 3 milligrams. Pepsin is dissolved in enough water to make a 10 milliliter solution. And we have the osmotic pressure of that solution is 0.162 torr. Calculate the molecular mass of pepsin. And then kind of to what we were saying before, right? Assume that this is a molecule so that the Van Hoff factor is 1, since we're talking about, right, an entire digestive enzyme. So see if you can calculate that now. Yeah. So the R is just a 0.0821 again, so I probably wasn't going to give it to you. Because, right, we usually just see 2 R's. It's either like the 8.34 when we're in energy land or the 0.0821 when we're in gas or Banhoff. So 0.0821 is generally what I abbreviate it, or it's like 0.08206, I think is a less. And so that's for Kelvin, ATM, liters, moles. I'd have to double check, but yeah. And then, yeah, so then you want to just plug it into our Van Hoff equation for this one, where our osmotic pressure is equal to, and like we said, our Van Hoff is just 1 for these cases, since we'll make it easy and just do non-electrolytes. So times our molarity times R times T. And then probably have to change this to ATM, right, since this is torr and we're in 0.0821 ATM gas constant land. Yep, so then you get this number, so 2.13. So now I'll just start to finish it. Times 10 to the negative fourth is equal to molarity RT. So now solve for molarity, right? Oops. Sorry, I didn't realize we over time now. So 0.0821 times our temperature, so in Kelvin, so 298. So then we get this for our molarity, right? Something pretty tiny. So 8.712 times 10 to the negative 6 moles per liter. And then, what do we say? So we put 3 milligrams in. And so now I like to set up a proportion to keep myself sane. And so basically, let's figure out how many moles that was. So our molarity multiplied by our new liters, so 0.001. So that means, right, we have that many moles. Oh, sorry, not 0.001, 0.01. All right, so then we get that we have 8.712 times 10 to the negative 8 moles, right, in our amount. So then we can take our 3 milligrams, so 0.003, divided by our moles. So we get our grams per mole of about 34,000. All right, and so I do realize we're over time, so I don't want to hold people. But that being said, right, I'll be here, and then I'll be doing makeup labs. So I think we're doing titration and anything else that we need to get covered. So quizzes. Oh, I forgot to take attendance on who was here today. All right, so I didn't grab a piece of paper, but would you guys like scribble your name somewhere just so I can give you, this is for your quiz credit. So don't leave, just sign your name so I know who is here, and then, right, you'll automatically get your quiz 15 and 16 credit, full points for being here, for reviewing. So like I said, just scribble your name down. I know most of y'all. And if you weren't physically here in lecture, just send me like an email like, hey, I was there. Just so we all get our participation credit today. And then like I said, I'll be here. I'll be answering questions. I won't leave this spot. So if you're still confused over here, we'll answer questions. No, I was going to say probably just hang on to them. That's why I'm like, just scribble your name down. I mean, I'm going to use that to input the grades.
How late will you be here?
I mean, till around like 4:30 or whatever. Yeah, but just email me, but I'll be in the lab. But yeah, just kind of touch base, just so I don't like disappear somewhere. But All right, any other questions online before I end this stream? So like I said, just email me. I think I kind of know who is here. So I know 2 people in the chat, but still just confirm with me so you can get your 1516 quiz credit. And then anybody else that was in the chat, just email me and let me know so you can get your credit. And then I have office hours today. I can be available tomorrow. So whatever you guys need. But I'm going to end the stream for now.